All right, let's get going. Valentine's Day. So we're going to talk about how you solve a system of linear differential equations when the eigenvalues end up being imaginary. So let's look at this example. Kind of want I'm gonna actually so I'm actually gonna do a different example just because. So I'll tell you all and I'll actually link to it. Grant has done this example already on video, and I think it's definitely worth watching. So I'm gonna do a different example and hope that I don't fuck it up. So because this process is a little bit confusing. So let's actually look at let's look at this situation. So let's say we have the following system of differential equations. We have dx dt equal to, actually it's gonna be right here, yeah. 4x plus 5y dy dt is equal to negative x plus 2y. And we're gonna solve this system of differential equations in the usual way, at least to start off with, by finding the eigenvalues, finding the eigenvectors, and then there's a little bit more to it. So, eigenvalues. Determinant of 4 minus lambda, 5, negative 1, 2 minus lambda. That's going to be 4 minus lambda times 2 minus lambda minus 5. If we simplify that, it's going to be lambda squared minus 2 lambda minus 4 lambda is minus 6 lambda plus 8 plus 5 equal to 0. It's going to be lambda squared minus 6 lambda plus 13 equal to 0. You might notice that this doesn't simplify or this doesn't factor. It might still have real solutions, right? So you just because it doesn't factor doesn't mean you necessarily have imaginary eigenvalues. You still have to like throw it into the oh my gosh, the quadratic formula and figure out what your eigenvalues are. So we plug this into the quadratic formula, we're going to get lambda equal to negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 13, all divided by 2, which ends up being 6 plus or minus the square root of 36 minus 52 is negative 16, all divided by 2. And now we can certainly see that we do have imaginary eigenvalues or complex eigenvalues. And we're going to get 6 plus or minus 4i all divided by 2, which is 3 plus or minus 2i. Something we'll talk more about probably on Wednesday next week because we don't have class on Monday because it's a 3-day weekend. Is how we know what kind of solution we have based on the eigenvalues. I know right now that since the real part here is positive, not negative, this is going to be an unstable equilibrium because we'll see this when we look at our solution. Our solution is going to get further and further away from 0 because you're going to have e to a positive number of times t instead of e to a negative number of times t. Let's go ahead and find the eigenvectors. So this might be the time where I would encourage you to do finding the eigenvectors in the setting a minus lambda I times your vector equal to 0. So to find the eigenvectors, and I would almost always start with the one with the positive imaginary part. So we're going to say, great, for lambda equal to, let's say lambda 1 equal to 3 plus 2i, we're going to have our a minus lambda I times our unknown eigenvector equal to 0. So that's going to correspond to saying, great. So a minus lambda I is a little bit messy. It's going to be 4 minus lambda, so 4 minus 3 plus 2i, and then 5, and then negative 1, and then 2 minus 3 plus 2i times the vector we're looking for. He likes to call it v1 and v2. I don't love that notation, but I will go with it anyway. And so then doing this, set this equal to 0, 0, you can use either equation. Now, in this situation, it kind of doesn't look like, it doesn't look at first glance like both equations give you the same thing, but they do. Let's actually explore that. So looking at both equations, we either get, all right, up here. So that's going to be a 1 minus 2i right there. And that's going to be a negative 1 minus 2i. Yep, minus 2i. Sorry, our equations are either 1 minus 2i times v1 plus 5 times v2 equal to 0, or negative 1 times v1 plus negative 1 minus 2i times v2 equal to 0. And both of those equations are going to give us the same relationship. Let's look at the first one, because I feel like the first one looks less messy. So in the usual way, I'm just going to isolate one of the things. I'm going to say from that first equation, 5v2 is equal to negative 1 minus 2i times v1. I would probably rewrite that as 5v2 equals negative 1 plus 2i times v1. And just like in the past, that's how I'm going to find my eigenvector. I'm just going to say, cool, the first component is the coefficient of the second component, and the second component is the coefficient of the first component. So I'm going to say that my eigenvector is going to be v1 is 5, v2 is negative 1 plus 2i. We're just talking about finding eigenvalues and eigenvectors when they're complex, and then finding the solution based on that. Now, here's what's nice about this. Although you don't actually really need to know it, the other eigenvector with the other eigenvalue is just the complex conjugate, meaning this eigenvector goes with this eigenvalue for lambda equal to 3 plus 2i. And it's also true that the other eigenvector is going to be 5, negative 1 minus 2i for the eigenvalue lambda equal to 3 minus 2i. And if you think about it, we could have gone back into our original equation and just changed every positive 2i to a negative 2i, which would have had the net effect of changing this positive 2i at the end to a negative 2i at the end. So you can kind of see how, yeah, that one change would carry through the whole way. But again, we don't actually really need to know that. Just so we can be confident about this, let's look at the second equation here as well, just so you can kind of be convinced that either equation is going to be good here. If instead I had used the equation negative 1 times v1 plus negative 1 minus 2i times v2 equal to 0. And if I brought, say, again, my, sure, let's bring, I don't know which one. Let's bring this one to the other side. So I have negative v1 equal to 1 plus 2i times v2. The eigenvector I would write now would be, it's going to look different for a moment. It's going to be, let's see, my v2 is going to be negative 1, and my v1 is going to be 1 plus 2i. And it's very bright, sorry. Do those eigenvectors look the same right now? No, they don't. But they are the same enough, meaning they are multiples of each other. So if you take this eigenvector, and I'm just going to multiply it by 1, yeah, be careful here, 1 minus 2i. So I multiply this eigenvector by the scalar 1 minus 2i. I end up getting, well, the second component is going to be negative 1 plus 2i. That's, by the way, how I picked it. I just figured out what I needed to multiply by negative 1 to get that part right there. And then 1 plus 2i times 1 minus 2i is going to be 1 squared plus 2i minus 2i, which cancels out, minus 4 times I squared, which is plus 4. So 1 plus 2i times 1 minus 2i is going to be 1 plus 2i minus 2i minus 2i squared, sorry, minus 4i squared. But 4i squared is negative 4. And minus negative 4 is plus 4, and 1 plus 4 is 5. So these eigenvectors, either equation you use is going to give you the right eigenvector. They might look a bit different because they're multiples of each other, and the multiple is usually an imaginary number, but they're still the same enough. Okay, so that's the easy part. Now here's the fun part. So to write the solution, well, one thing I want to point out is that whether you're using this eigenvalue or this eigenvalue, the real part's the same. So when I start trying to throw this into my e to the lambda t times v, I don't need both of them because I feel like I'm getting ahead of myself a little bit. Let me do it and then I'll kind of circle back to why we didn't need both of them. But we only really need our solution to look like, I guess I need to see one. Let me double check I'm not doing something stupid here. Just 1 second. Let me make sure I'm not making a dumb error here. Yeah, cool. I'm good to go. All right, cool. So our solution is going to be C e to the lambda t times v. Just v. I'm just calling it v for now. Just like before, except we only have one piece instead of two pieces. All right, so here's what we're going to write. And this is where things are going to get a little bit computationally gross, but not the worst thing ever. So this is going to be x bar equal to c e to the, I like using the one with the positive eigenvalue, the positive imaginary part, but it doesn't actually matter which piece you pick. So it's going to be e to the 3 plus 2i times t times our eigenvector, which is 5, negative 1 plus 2i. We're going to break the e to the 3 plus 2i times t part up into two pieces. It's going to be e to the 3t times e to the 2i times t. I'm specifically going to write that as e to the I times 2t. Just to make something extra obvious. I want him to do that. Okay, so here's where Euler's formula jumps in, right? The formula we talked about last class with the e to the I theta. Oh, we have e to the I times something that's going to act like our angle. So as a reminder here, e to the I times theta is cosine of theta plus I times sine of theta. And in this example, 2 times t is playing the role of theta. So we're going to rewrite this as c e to the 3t times, it's kind of gross, cosine of 2t plus I times sine of 2t times the vector 5, negative 1 plus 2i. And he did something kind of different in class where he is like, you basically took your eigenvector and then busted it apart into like an imaginary and a complex part, and then kind of regroup some things. And it's kind of more work than you really need to do. So I'm trying, the example I'm showing you, I'm trying to show it to you kind of in the least amount of steps possible, or at least the least amount of mental work possible. So this is what I want to mention here though, like if I had the e to the 3t, if I had my other eigenvalue, 3 minus 2i, I would have ended up with e to the 3t times cosine of negative 2t plus I sine of negative 2t. And that wouldn't have really changed the fact that I still had an e to the 3t here, right? I still would have an e to the 3t. It's not like it's an e to the 3t and e to the negative 2t or something like that. So that's why we don't need both pieces, unlike previously. We're going to end up generating both pieces just with this one piece, which is kind of weird. So now we're just going to do the multiplication, which does get a little bit gross. So we're going to leave the c e to the 3t out in front, but we're going to distribute the cosine 2t plus I sine 2t to both the 5 and the negative 1 plus 2i. And specifically for the negative 1 plus 2i, it's going to be a little extra gross because it's going to be like a foiling situation, but such is life. So we're going to get c e to the 3t, and then the vector is going to be, so I'm going to have 5 times cosine of 2t plus 5i times sine of 2t. That's my first one. And the second one's going to be a little bit longer. Let's see what I've got. So I've got cosine 2t times negative 1, so negative cosine of 2t. And then 2i times cosine of 2t. And then I times negative 1, I sine of 2t times negative 1, so negative I sine of 2t. And lastly, I sine of 2t times 2i, so 2i squared sine of 2t. And then your job is basically to break this up into the real parts and the imaginary parts. So we're going to say this is c e to the 3t times. So in the first component, the only real part is 5 cosine 2t. In the second component, there are two real parts. There's the negative cosine of 2t, and there's also the 2 times I squared times sine of 2t, because I squared is equal to -1. So this part's going to be actually a -2 times sine of 2t. Plus, then we have the imaginary parts. We have our 5i sine of 2t, and I'm going to pull the I out in front because that's pretty typical. So I times 5 sine of 2t. And in the second component, we have, let's see, a 2i cosine of 2t. So we have a 2 cosine of 2t. And we have a negative I sine of 2t. So we have a minus sine of 2t. And now here's kind of the dicey move that we make that feels a little shady, but works. So we're essentially going to distribute this constant to each of these two vectors. So the constant times this vector, we're just going to say it's multiplied by a constant. We're going to call it C1. So we're going to say distribute here and here. So we're going to say we have e to the 3t times, we're going to have C1 times our first vector, 5 cosine of 2t, negative cosine of 2t minus 2 sine of 2t, plus our constant times I is still a constant. It might be imaginary, but it doesn't matter. It's still a constant. It's not the same as the first constant, so we're going to give it a different name, C2. Times 5 sine of 2t, 2 cosine of 2t minus sine of 2t. And that's our general solution. Not too terrible. Says the man who's been doing it for a number of years and finally wrapped his head around it. So yeah, it's still kind of terrible. But so because they're used to kind of like, I think when we taught this before, we used to kind of approach it kind of trying to do the other thing that was done in class, which kind of actually feels more like a shortcut in some ways because you're kind of skipping the part where you're actually like multiplying it all out. But honestly, I think after having seen this for a number of years, this is kind of the easiest way to do it. Find your eigenvalue, find your eigenvector. You only need one eigenvalue and one eigenvector. Usually we use the eigenvalue that has the positive imaginary part, but it doesn't actually matter. And then you do this. You just throw it into the usual formula. C e to the lambda t times v. And then you multiply it all out as much as you can. Group the real parts together and the imaginary parts together. There's a word he keeps using in class that I can't remember what it is, but it's like we bring everything together. But it's like I keep hearing him say there's one where I can't remember what it is now, but like there's something he says that really sticks out to me. Like we accumulate, I think he says accumulate a lot or something like that. Anyway, we accumulate things together and we eventually get to this final solution. But we could add on another layer of intricacy by then saying there's an initial condition. So let's do that. In this case, especially, it is so I'll say occasionally with these problems, they make the initial condition something other than when t is equal to 0, and it's usually trash because like then you have this e to the something being not 1, and then finding C1 C2 is extra gross. It would be even extra gross here if t wasn't 0, because then these things wouldn't work out nicely. So we're going to make up something. Let's say our initial condition is that x of 0 is equal to, sure, I'll just wing it here. X of 0 is equal to 3. Y of 0 is equal to -2. Let's see what happens with that initial condition. Okay, so what I should say, right, this is our general solution here. So I'm going to write over here, this is our x of t, y of t. Yeah, and I might actually do a little more with this. So yeah, we'll find our particular solution and then we will come back and talk about how this might look. So plugging in 0 for t and 3 for x and -2 for y. On the left-hand side, I have 3, -2. On the right-hand side, I have e to the 0, which is 1, which I'm not going to write. C1 times cosine of 0 is 1, sine of 0 is 0. So we have 5 for that, and then -1 minus 0. And then we have C2 times 5 times 0 is 0. And C2, let's see, times that's going to be a 2 times 1. Ah, yes, this is convenient. And I think this happens actually quite a bit, is that you're going to get a 0 in one of your spots. If there's a 0 in one of at least one of these spots, it makes it really, really easy to figure out what C1 and C2 are. So I know that 3 is equal to C1 times 5. Which means C1 has to be 3/5. Because there's a 0 there, 0 times C2 plus 5 times C1 has to equal 3. So I automatically get to figure out C1 without having to do really anything. And then I can go back and find C2 using the second equation. So my second equation is negative 2 is equal to negative 1 times C1 plus 2 times C2. But for C1, I'm going to plug in the value I just found, which was 3/5. And then I can find C2, let's see, negative 2 plus 3/5, okay, negative 10/5 plus 3/5 is going to be negative 7/5 is equal to 2 times C2. So it looks like C2 is going to be negative 7/10. So here our particular solution. Particular, I think there's an R. I don't, doesn't matter. It's not a spelling class. Particular solution is going to be that x of t, y of t is equal to 3/5 times the vector 5, -1 plus negative 7/10. I should just write in minus, but I put a plus sign times the vector. Hold on, whoa, I got I skipped up these two. I do this thing, not this thing. Sorry. That's very, very incorrect. It's all gonna fill on that page too. Sorry about that. Oh well. Sorry, the particular solution actually here, plugging our C1 and C2 back into our general solution up there, not to this garbage here. Our particular solution is going to be that x of t, y of t is equal to e to the 3t times C1, which is 3/5, times this vector, 5 cosine of 2t, negative cosine of 2t minus 2 sine of 2t, minus 7/10 times that vector, which is 5 sine of 2t, and then 2 cosine of 2t minus sine of 2t. It is kind of worth noting a couple things here. So thing one, as time goes on. So as time goes to infinity, what's going to happen to e to the 3t? It's also going to get infinitely large. So certainly things are spiraling out of control here. Pun intended. I know it's not, well, it might not be a pun yet because we haven't talked about what the solution looks like here, but the solution is going to be a spiral. So what's happening here, and I'm not great at drawing this, so I'll probably use some sort of graphic names in a second here. But if we actually look at each solution individually, check it out. X of t is equal to the top part, so it's going to be e to the 3t times 3/5 times cosine of 2t minus e to the 3t times 7/10. Oh, I forgot the 5 there, sorry. 5 times 7/10 times 5 sine of 2t. So I guess I could have made it look nicer. This is equal to 3e to the 3t cosine of 2t minus 3.5 or 7/2 e to the 3t sine of 2t. So what's happening here is this thing is going to oscillate because, right, when time equals 0, sure, cosine is 1 and sine is 0. So you're going to get 3e to the 0. But then like over at, say, when time is equal to pi over 2, or pi over 4, cosine is going to be 0, sine is going to be 1. So then this negative part's going to command it, and actually it's going to dip down below. So we have this thing here, and I'm going to try and draw it here. But basically, if you were to graph x of t versus t, you're starting out with an initial condition of 3, but then you're wildly oscillating. Because as time goes on and on and on, this value gets bigger and bigger and bigger, and these two values bounce back and forth between 1 and -1. And the similar thing is true for y of t. Y of t is also going to do the same sort of thing. If we simplify this a little bit, y of t is even worse. Ugh. It's okay. Oh yeah, all right, yeah, sure. So let me do some, fine. So it's e to the 3t times, what do we got here? I've got 3/5 times negative cosine, so -3/5 cosine of 2t, and then minus 6/5 sine of 2t. And then I also have minus 7/10 times 2, so minus 7/5 cosine of 2t. And minus is plus 7/10 sine of 2t. It's kind of terrible. You could probably simplify that. Yeah, fine, I'll simplify it. -7/5 minus 3/5 is -10/5, which is -2. So I have e to the 3t times -2 cosine of 2t. And I have e to the 3t times, let's see, -6/5 or -12/10 plus 7/10 is -2/10 or -1/5. So -1/5 sine of 2t. Sure. Yeah. That's not right. My brain is not working right. -12/10 plus 7/10 is -5/10, which is -1/2. Doesn't really matter all that much because usually you don't do this work anyway. Okay, so in a similar way, y of t is also doing some kind of crazy oscillating. If we plug in 0 for t, we start with a value of -2, because -2 times cosine of 0 is 1, -2. So we're starting down here at -2. But then, again, as time goes on and on, these both go back and forth between 0 and 1 and -1. And so you're either going to get this part here or this part here, bouncing up high, bouncing down low. So you get some sort of funky oscillation, which I'm not really good at drawing. What that means for the solution is that, yeah, as time goes on and on and on in your two-dimensional plane here, right, your phase, your direction field, right, you move away from the origin because x and y are both getting larger and larger and larger, but they're doing it very wildly, right? X and y are both very, very positive large, very, very negatively large. Maybe one's positive, one's negative. So you're kind of all over the map, which ends up being a spiral. So let's look at what this looks like, because I'm not very good at graphing it here, but let me pull up. Yeah, I think we want this one. Let's see, graphing. Where's my cool grapher here? Yeah, I want that one. Okay. Let's see if this one works for us. Oh, what's going on there? Okay. So remember what our differential equations were. They were dx. So let's see, so click on, oh, wow, where's my cursor? Sorry, where's my cursor? There it is. Okay. So click on this and then write our differential equations. So they were going to be 4 times x plus 5 times y. And then the second one was -x plus 2y. I think that's all we can do. Cool, let's hit enter. Well, y doesn't look like anything. Why doesn't it look like anything? And I need to zoom out some weird way. Let's.
This one not the cube in the asterisk?
I don't. You know what? Maybe it does. I was hoping it didn't because I was feeling kind of lazy, but you might be right. 4 times x plus 5 times y. And then we have -x. Let's be extra careful. -1 times x plus 2 times y. Nope, still looks super funky. I don't know why this wouldn't be looking. I mean, I feel like I'm very zoomed in here weirdly, but It seems strange. I don't know why. Usually this one is not problematic. Sorry about that. It was really, yeah, it says multiplications and pride. Maybe if I let's change this. Now, maybe. No, I don't. Wow, okay. Just you're like, nope, no more. I don't know why. That's bizarre. Well, look, fine. We'll look at the other ones. So we can at least see what it looks like. But what I was hoping to give you was also the time plot, so you could see how they were like wavy like this, like not just by me drawing them. But if we look at the other one here, sorry, I don't know. I'm gonna have to go play with that later. Um, look at this other one. I'm gonna look at dx equal to 4 times x plus 5 times y, and dy dt is going to be negative x plus 2 times y. Graph it. It's a spiral, and it's an unstable spiral, right? We're definitely going outward away from the equilibrium. And if you pick any point you start with, like if I, click here, you can see, oh yeah, we are spiraling outwards. Um, yeah, interesting. I think this doesn't look as spirally as some other spirals sometimes look. But it's no, it's a spiral. A spiral. I feel like I'm doing something crazy here, and let me just double check something. That's fine. Yeah, yeah. Nope, that should be 4 times x plus 5 times y, negative x plus 2 times y. That should be right. Yeah, okay. So, why don't you look more spiral? I'm annoyed it doesn't look as spirally as I feel like it should. Um, yeah, not very spirally. Because usually when you have a spiral, it actually like you see it start to kind of like loop around on itself with these graphs often. So yeah, I'm a little bit perturbed. So this is certainly an unstable spiral. And we mostly know that based on the fact that it's a spiral because our eigenvalue is complex. It's unstable because the real part, oh, sorry, yeah. Because the real part is positive. So since our eigenvalue was, there were 2 plus or minus 3i, I believe. Yeah, 3 plus or minus 2i, sorry. And the fact that that 3 is positive, that's what's making it unstable. So, questions, comments, concerns, observations. The process is a bit lengthy, but it is very doable. So I would say, as far as, so I did kind of a lot more than I needed to here, or a lot more than you would have needed to do. We certainly should have and could have stopped when we got to saying that our general solution was this, and our particular solution was this here. Oh, sorry, this. So here's our general solution. And here is our particular solution down here. Should we do another one? Yeah, let's do another one. Okay, I'm gonna grab one from the textbook. I think it's worthwhile. Oh, and here's the attempt. Sorry, I forgot what the attempt before. No. Okay, sure. Alexa, Nathan, and last name is Polito, but I'm not sure. Is it Blanca? Okay. Sorry, where'd you go? Okay, yeah, examples. So let's look at this one. Sure. So here is one of the problems he assigned in order here. Oh, I know that. There's one other thing I wanted to say about this problem. Sorry. So sometimes they'll ask you which way the spiral is turning, whether it's clockwise or counterclockwise. And there is a way to tell based on the matrix, but I don't ever remember what it is. So I'll point out that our matrix here was the matrix. Where'd you go, matrix? Why are my papers out of order? All right. There we go. It was 4, 5, -1, 2. And the way you can tell which way, so we know it's a spiral based on the eigenvalues, and the way you can find which way it's going to turn is by just plugging in a couple points. And remember, this is representative of our differential equations. Dx dt equals 4x plus 5y, and dy dt equals -x plus 2y. I'm a fan of looking at the 4 points 1, 1, -1, 1, 1, -1, and -1, -1. So if I plug in the point 1, 1, so at the point 1, 1, my dx dt is going to equal 4 plus 5, and my dy dt is going to equal -1 plus 2, which means I'm going over 9 and up 1. So I'm pretty much going almost straight to the right. And then I'm going to go down here to 1, -1. So at 1, -1, my dx dt is going to be 4 minus 5, which is -1. And my dy dt is going to be 1 minus 2, which is -3. So I'm going left and down, but more down than left. I could probably stop right here. I'm pretty sure this thing is going clockwise. But in fact, the thing about these points here is they're always just mirror images. So like this one down here is going to be the mirror image of that one up there. It's going to be going that way. And this one here is going to be the mirror image of that one there. It's going to be going that way. Oh yeah, it looks like it's a clockwise spiral. All right, let's look at one more example while we have time. Sure. So this next one is number 27 from section 10.2. And we're given the following. The matrix is, yes. Oh, sorry, my brain. Apologies. What going? Sorry, did you guys see this, the clockwise stuff I did? Okay, I wonder what happened. That's weird. Sorry, we have the matrix 2, -5, 2, 1. And we have initial conditions 1, 1. Okay, so we're going to solve the system by finding all the things. So first, the eigenvalues. Determinant of 2 minus lambda, -5, 2, 1 minus lambda is equal to 2 minus lambda times 1 minus lambda minus -5 times 2, which is going to be lambda squared. Minus lambda minus 2 lambda is -3 lambda plus 2 plus 10. Doesn't factor. So we know our eigenvalues are going to be -3. I should have unexciting. It's also I know already that this thing's going to be an unstable spiral again, because my real part of my eigenvalue is positive, such as life. So -3 plus or minus the square root of -3 squared minus 4 times 12, all divided by 2. It's going to be 3 plus or minus the square root of 9 minus 48 is -39 all over 2. So this is going to be 3/2 plus or minus I times root 39 over 2. Much less nice. Sometimes you get not very nice eigenvalues. Okay, eigenvectors, we're only going to find one of them. So for the eigenvalue with the positive imaginary part, it doesn't really matter. So for lambda equal to 3/2 plus I times root 39 over 2, we're going to find the eigenvector. And I do recommend finding the eigenvector in the other way. So we're going to set our A minus lambda I times our vector equal to the 0 vector. So our a minus lambda I is going to be pretty gnarly here. It's going to be 2 minus 3 halves plus I root 39 over 2, -5, 2, and 1 minus 3 halves plus I root 39 over 2 times the eigenvector we're looking for equal to 0, 0. You can use either equation. I'm usually partial to using the first one. So the first equation, and I'm going to simplify it just a little bit. My first equation, this 2 minus 3 halves is a positive 1/2. So that's 1/2 minus I times root 39 over 2. So what I have here is that times V1. So I have 1/2 minus I times root 39 over 2 times V1 minus 5 times V2 equal to 0. I would bring the minus 5v2 to the other side. So 1/2 minus I times root 39 over 2 times V1 is equal to 5 times V2. In this case, I might make a slightly different choice than I usually do. Instead of picking V2 equal to that and V1 equal to that, I might multiply both sides by 2 first. I would rather not have fractions in my eigenvector. So if I multiply both sides by 2, I have 1 minus I root 39 times V1 equal to 10 times V2. So my eigenvector here is going to be the vector where V2 is equal to 1 minus I root 39 and V1 is equal to 10. We could have also made these choices first and said V1 was equal to 5 and V2 is equal to 1/2 minus I root 39 over 2 and then multiplied the whole vector by 2. That's probably actually the more sensible way to get there, but it's not what my brain was thinking. Okay, there's my vector. Now we have to write out the whole solution. So the solution, again, very generic. The solution is x of t equals c e to the lambda t times your vector v. It's just that we're plugging in these gross things. So that's going to be c e to the lambda was our 3/2 plus I root 39 over 2 times t times our vector, which is going to be 10, 1 minus I root 39. After this step, your next step is to break apart the e into 2 pieces so that you can use Euler's formula. So this is going to be equal to c. We're going to have e to the 3/2 t, which is telling us about the instability, right? We know as time goes on, our values of x and y are going to get larger and larger and larger. And then we're going to have the e to the I times root 39 over 2 times t. I would put the not I part in parentheses and think of it as I times root 39 over 2 times t times our stupid vector over here. Okay, now we have to throw Euler's formula at this e to the I times something gross and say, cool, e to the I times something gross is going to be cosine of that something. So cosine of root 39 over 2 times t plus I times sine of the same root 39 over 2 times t. All times still the vector 10, 1 minus I root 39. Now we multiply it all out. Fun times for everyone. So we multiply it all out and we get c e to the 3/2 t. And we're going to have, so each thing here is going to get multiplied by 10 in the top spot. So we're going to have 10 cosine of root 39 over 2 times t plus I times 10 times sine of root 39 over 2 times t. The bottom part's a little bit grosser. Sometimes you luck out and each piece only has like you don't have like a 1 minus, you just have a minus there, but that's not the case here. So in the second part, and I shot myself in the foot here by closing my bracket too soon here, but multiplying the second part, I'm gonna have cosine times 1, so cosine of root 39 over 2 times t. And then cosine times negative I, no, yeah, negative I root 39. So it's going to be minus I root 39 cosine of the same thing. Sorry, it's a little bit messy here. And then multiply the I sine by that. So I sine times 1 is going to be plus I times sine of root 39 over 2 times t. And then finally, I sine of stuff times negative I root 39 is going to give us a minus I squared root 39 sine of root 39 over 2 times t. And then your next job is to break this up into two vectors, one with just the real pieces and one with just the imaginary pieces. So we're going to rewrite this as, this is where it gets gross. C e to the 3 halves t times, the first vector is going to be the 10 cosine of root 39 over 2t. How many times do we say that today? And the second component is going to be the cosine part here, the cosine of root 39 over 2t, and also the negative I squared times root 39 times sine of root 39 over 2t, because negative I squared is negative negative 1, which is positive 1. So it's going to be plus root 39 sine of root 39 over 2t. And then the second component, or the second vector, sorry, is going to be, I'm going to pull out the I, and in the first entry, it's going to be I times 10 times sine of whatever. So the I comes out and you've got 10 times sine of whatever. And second component, you have negative I times root 39 cosine. So you have negative root 39 cosine of root 39 over 2t, and then plus I times sine of the same thing, so it's going to be plus sine of root 39 over 2t. And again, the reason I'm not writing the i's is because I already factored the I out. We're one step away from the general solution. This is the part that always feels a little bit like we're doing something a little shady. We're going to multiply the c by both of those vectors there. And then c times 1, we're just going to call that c1. And c times I, we're just going to call that c2. So we're going to rewrite this, and it's a lot of writing. We're almost out of time, but not quite. So we're going to say that our general solution is going to be, it's going to be c1 e to the 3 halves t times this first gross vector, 10 cosine of root 39 over 2t. And the second component is cosine of root 39 over 2t plus root 39 times sine of root 39 over 2t. What a gross problem to have assigned. Plus c2 times e to the 3 halves t times the vector 10 sine of root 39 over 2t, and then minus root 39 cosine of root 39 over 2t plus sine of root 39 over 2t. Bonkers. But not undoable, right? Yes, it seems terrible, but if you practice it a few times, it'll be pretty doable. It's just a lot of steps. Okay, now we have 1 minute left, but let's go ahead and find the particular solution. So I'll remind you that we were told that x0 was equal to 1, 1. And this is our general solution here. Sorry, this is our x of t, y of t. So if we plug in 0 for t and 1 for x and 1 for y, here's what we get. We get 1, 1 equal to c1 times e to the 0, which is 1, times 10 times cosine of 0. Well, cosine of 0 is 1, so we get 10. And cosine of 0, which is 1, plus root 39 times 0. Cool, that turned out to be not super terrible yet. Plus c2 times e to the 0, which is also 1. And then 10 sine of 0 is 0. And we do get a negative root 39 times cosine of 0, which is a negative root 39. Couldn't be avoided. I think almost every time when you solve these, with maybe rare exception, you're almost always going to get a 0 in one of these 4 spots. So everybody should be able to tell me right now what C1 is equal to. It is a fraction. It's 1 over 10. C1 has to be 1/10 because 1/10 times 10 plus whatever C2 is times 0 has to equal 1. So it's very, very straightforward to find C1 here. C1 is 1/10, and then C2 is a little bit grosser, but for finding C2, it's going to be 1 is equal to C1 times 1 plus whatever C2 is times negative root 39. So it looks like 1 minus 1/10, so we're going to get 9/10 is equal to C2 times negative root 39. So C2 is unfortunately 9 over 10 times negative root 39. So let's put the negative out front. And then I suppose someone would probably want you to rationalize this. So we should write it as negative 9 root 39 over 10 times 39. And then we can cancel a 3. So we end up getting negative 3 root 39 over 130. It's kind of terrible. And then I'm not going to write it out since it's 202, but to find your particular solution, you would just plug in this value of C1 right here, this value of C2 right there, and then write out that whole gross thing, and that would be your particular solution. This example does feel extra heinous, kind of, just because the numbers are kind of gross. But yeah, I do think it's good to practice these. Because it sounds, I mean, he certainly assigned a few of them. I don't know if they're going to show up on an exam, but they could. So yeah. Not impossible, just takes sustained effort. But this is certainly better. I think this is a more direct way of doing it than all the things he said in class about G and H and U and V and W. So I would do it this way.